in this video we're looking at fuels, and we're specifically going to look at alkenes, alkynes and benzene. So we're going to explore aromatic hydrocarbons and the names, formulas and isomers of alkenes and alkynes. So let's jump straight in and look at alkenes. So alkenes are a family of hydrocarbons where two carbons are linked by a double bond. So the functional group is C double bond C, and these are now unsaturated. If you remember from our alkanes video, we said alkanes were saturated because they had they just had single bonds present, but alkenes have a double bond, so that makes them unsaturated. And the key part here is the E in alkenes. So for alkenes, some sample names, formulas and structures. Ethene has a formula of C2H4, and if you draw that out, you can see here you've got two carbons connected by a double bond. So carbon can only have 4 bonds, so that must mean that there is 2 hydrogens attached off each carbon. Next one is propene. So eth prop. Prop means that there's 3 carbons and there will be 6 hydrogens. And the important thing to note with your propene is if it's prop 1-ene, your double bond goes on the first carbon. If it's prop 2-ene, it starts on the second carbon. So if we look at butene then, it's C4H8. So this is but 1-ene that I've drawn here. If the double bond, instead of it being here, if it started on carbon 2, it would be called but 2-ene, and if it started on carbon 3, it would be called but 3-ene. And we'll see this when we do some examples. If we look specifically at the chemical formula, we can see that each of our molecules differs by 1 carbon and 2 hydrogens, so they are part of the homologous series as they differ by a CH2 unit. So if I write down the formulas that we met on the last slide, you should be able to see a trend in the formula, general formula for alkenes. So if you look here, the number of hydrogens that are present is twice the number of carbons. So the following is your general formula. It's CnH2n, where n is the number of carbon atoms. So just to quickly do, if I had n equals 2, that would mean that I would have C2H4, which is ethene from our last slide. The systematic naming for alkenes is pretty similar to the alkanes. You identify your longest chain of carbon atoms. You identify any substituents. However, when numbering with the alkenes, you start numbering with the end nearest the double bond and note the carbon on which the double bond starts. Then you indicate the position of your substituents and you assemble the name listing them alphabetically. So let's try an example. So let's take a look at this example here. Step 1 is to identify your longest carbon chain. So I can see 1, 2, 3, 4, 5. So I have 5 carbons in my longest chain. So that means I'm dealing with pent. I look now and I see that there's a double bond present, so I know that I'm dealing with pentene. Step 2 is to identify any substituents. So I can see straight away I have a chlorine substituent, so that will be chloro. I have then 2 bromo substituents, so it will be bromo. The next thing to do is to number your carbon chain, ensuring you number it that the carbon that the double bond starts on has the lowest number. So there's 2 ways that we could number here, and that is 1, 2, 3, 4, 5, or we could go 1, 2, 3, 4, 5. So going from left to right, we see that the double bond starts on carbon 2, and going from right to left, it starts on carbon 4. So we are going to go with our top set of numberings. So I'm just going to rub out the bottom ones now. And it's important to note the carbon at which the double bond starts. So it starts at 2. So we know that we are going to have pent 2-ene. That's how you indicate where the double bond is in an alkene. So step 4 now is to indicate the location of your substituents. So I know it's going to be 2-chloro, and I know it's going to be 4,4-dibromo. And I know it's going to be 4,4-dibromo because there's 2 bromos, and that's why it's di, and it's 4,4 because the bromines are both on the same carbon. So now let's assemble the name. So it's going to be 4,4-dibromo because bromo comes before chloro in the alphabet. So 4,4-dibromo 2-chloro-pent-2-ene. And that is your structure now named. So let's look at another example now of how to name a molecule given its structure. So step 1 is identify your longest carbon chain. So here I can see my longest carbon chain is either 1, 2, 3, 4 or 1, 2, 3, 4. So I know it's definitely 4 carbons, so it is bute, and I can see that there's a double bond present, so it's going to be butene. The next thing you need to do is identify your substituents that are present. So I can see I have a methyl, and a chloro. Next thing to do would be to number your carbon chain. So let's number it in all the ways we can. It could be 1, 2, 3, 4, or 1, 2, 3, 4. So you must always number giving the double bond the smallest value. So here I can see it. I actually need to number from left to right because that gives the first carbon of the double bond 1 versus 4. So I'm going to rub out the numbers here on the bottom, and I can say for step 3 then that it's going to be but1-ene. Step 4 then, number your substituents. So I can see that the methyls are on 3, so it's 3,3-dimethyl. And I can see that the chloro is on 2, so it's going to be 2-chloro. So now assemble your name. It's 2-chloro, 3,3-dimethyl, but1-ene, and that's your structure. So let's try and draw the structural formula now given the name. So step 1, always identify your longest carbon chain. So here I can see that it is pent, so that means there is going to be 5 carbons. Step 2 is to identify your substituents. So I've got 2 ethyls, and that's all. Step 3, identify, number the longest carbon chain so I know it's pent. The location of the double bond is on the starts on the first carbon, and that's from there we have all the information that we really need. So I can see that it's pent 2, 3, 4, 5. I know that the double bond starts on the first carbon, and I know that ethyl goes on carbon 2 and ethyl goes on carbon 3. Formula that is required. For isomers, the definition is the same as was in the alkanes video, and we're just going to look at the isomers of butene. So when we're talking about butene, unless told otherwise, you always assume that the double bond is on the first carbon. So something is always an isomer of itself, so that means our first isomer is but1-ene, and you can see that it's drawn there. Now, moving the double bond along your carbon chain in alkenes actually creates isomers. So our second isomer will be but2-ene. Now, if I was to move this double bond onto this carbon here, that would mean that that would actually be moving back to carbon 1 because you would number it in the opposite direction. So at this point now, you should be looking at swapping groups. So I'm going to swap this methyl group here with this hydrogen. You must swap it with a hydrogen in the middle of your carbon chain, and what that will give you is it will give you 2-methyl prop 1-ene. So we'll see that if I shade these in for you, that this blue is now here and that this hydrogen is now here, and that's caused your carbon chain to decrease by 1 and your double bond remains where it is. For properties of alkenes, ethene, propene and butene are all gases at room temperature, and most other alkenes are liquids at room temperature. Alkenes are insoluble in water, so they are nonpolar. And our cyclic alkene is cyclohexene, and with our double bond, the double bond can go on any of the carbons here. You just need to make sure that the carbon either side of the double bond only has 1 hydrogen coming out of it, because carbon can only have 4 bonds. We can see here 1, 2, 3, 4. So moving quickly on then to alkynes. Alkynes are the family of hydrocarbon that have their 2 carbon atoms are linked by a triple bond. So the functional group for an alkyne is C triple bond C. Or structural formulas, but you do need to know the properties. So the properties of alkenes: they're excellent fuels, they're gases at room temperature, and a use of alkenes is oxyacetylene welding. So up until this point with our alkanes video and alkenes and alkynes, we've been dealing with aliphatic hydrocarbons, and an aliphatic hydrocarbon is an organic compound that consists of open chains of carbon atoms and cyclic or rings that resemble them in chemical properties. But what we're going to briefly touch on now is we're going to touch on aromatic hydrocarbons. And aromatic hydrocarbons, they contain something called a benzene ring. So let's look at what this means in closer detail. So if we look at benzene itself, we can see that benzene was first isolated by Michael Faraday in 1825, and it has the molecular formula C6H6. Now, benzene, if you look, you can see here that there's double bonds, and we can see that they can change location. So the true structure of benzene that we draw down is this structure here that has a ring. So let's explain this. So despite being highly unsaturated, benzene actually behaves as a saturated compound, and you would expect it not to, due to the double bonds that seem to be present in it. However, it is very unreactive. And it was originally thought that the structure of benzene consisted of the alternating double single bonds that were shown in the last slide. But upon a closer observation, it was actually found that the carbon-carbon bond lengths were similar. So this means that it actually couldn't be alternating double and single bonds, because double bonds and single bonds have different lengths. So this alternating double single bond idea was quickly quashed. So the bond lengths in benzene are actually in between single and double bond length. They're in the middle. So they neither have the length of a double bond or the length of a single bond. They're in between. So this led to undertaking the bromine test. And undertaking the bromine test, there was no rapid decolorization or no rapid color change from our red color. So that meant that there was no carbon-carbon double bond present. So what there actually is there is 6 equivalent carbon-carbon bonds, giving the following ring structure. and the ring indicates something called delocalized electrons. So basically, rather than having this structure where the double bonds can alternate, as I indicate for you here, they actually have this ring structure because the electrons are basically moving so quickly that we get this delocalized electron cloud. So the electrons are not really attached to any of the carbons in particular because they form this delocalized cloud. And this is what gives the benzene molecule extra stability, and that accounts for its lack of reactivity. And this is explored in greater detail in the bonding videos. For the properties of benzene, the angles in benzene are 120 degrees, so the carbon angles. Benzene is an excellent solvent, but it is highly toxic. And two useful forms of benzene are methylbenzene and ethylbenzene. So that's it for this video. Have a read over the learning intentions to check you understand everything we've gone through.